Welcome to The Explainer. Today, we're diving straight into a high-stakes, real-time medical mystery. We spend a lot of time analyzing sweeping global health trends, but today, we're zooming in on a very specific, highly elusive pathogen that has quietly challenged the brightest minds in virology for decades. It's a story about a deadly virus, a truly tricky vaccine development process, and what it all actually means for our vulnerability to future outbreaks.
50%. I want to just let that sink in for a second. 50%. We're all too familiar with viruses that have fatality rates of 1 or 2%, which, are devastating enough on a global scale. But certain strains of the Hantavirus, they literally have a coin flip fatality rate of up to 50%. It's staggering. When a pathogen is this dangerous, even a tiny cluster of cases instantly triggers alarm bells across the entire global medical community. And honestly, that brings us right to the real-world threat we're looking at today. Recently, an outbreak of Hantavirus threw a massive spotlight onto this pathogen when it struck the cruise ship MV Hondius. The numbers are small, but they are incredibly severe. 3 confirmed cases resulting in 1 death, and among 5 suspected cases, 2 more tragic deaths. So this isn't theoretical, right? This is an active crisis. Health officials, including the World Health Organization, had to absolutely scramble to evacuate and test passengers. But to really get why this specific outbreak is causing so much anxiety, we need to look under the hood at the biology. Let's start with understanding the Andes virus. So not all hantaviruses behave the exact same way. And the Andes strain, the one responsible for the cruise ship tragedy, has some seriously concerning tricks up its sleeve. First, just to set the baseline, Hantavirus is a zoonotic virus. Basically, that's an animal-borne virus that manages to jump or spill over into humans. The crucial point here is that zoonotic viruses are inherently unpredictable. Virologists liken this unpredictability to what we recently saw with the monkeypox virus. They hide out in animal reservoirs, mutating, circulating quietly, until suddenly the conditions are just perfect for them to cross over into us. Now, here's why the MV Hondius outbreak is so alarming. It comes down to a terrifying exception. Typically, a person catches a hantavirus by breathing in airborne particles from rodent urine, droppings, or saliva. It's an environmental exposure that usually just stops right there. The infected human doesn't pass it on to anyone else. But the Andes strain, it completely breaks that rule. It is actually capable of human-to-human transmission through close contact. And when you drop a strain capable of human-to-human spread inside the highly confined environment of a cruise ship, well, you can easily see why health authorities were on high alert. Which brings us to our next point, the climate change connection. You're probably wondering, are these outbreaks going to start happening more often? Virologist Jay Hopper points out a fascinating, if not pretty concerning, macro-level chain reaction. Step 1. Climate change is actively altering natural habitats. As temperatures and weather patterns shift, the environments where animals thrive change right along with them. Step 2. This causes rodent populations, which are the natural reservoirs for hantavirus, to shift their geographic footprints. And step 3. This inevitably leads to increased overlap with human populations. As rodents move into new areas or as we expand into altered rodent habitats, the opportunities for that zoonotic spillover absolutely skyrocket. So a warming planet is quite literally bringing this 50% fatality virus closer to our doorsteps. So let's look at what we're doing about it, the 30-year vaccine quest. You'd think with a threat this lethal and potentially growing, we'd have a vaccine locked and loaded, right? Well, the U.S. military has definitely been trying. Because these viruses are rodent-borne and pose a massive risk to deployed troops, the military has been highly motivated to stop them in their tracks. The U.S. Army Medical Research Institute of Infectious Diseases, USMRID, has actually been spearheading hantavirus vaccine research since the 1980s. In the 90s, the stakes got even higher when new strains causing severe respiratory disease were discovered, the sin nombre virus in the U.S. and the deadly Andes virus down in South America. Decades of painstaking research have led us to where we are today, with scientists finally pushing a vaccine into Phase 1 clinical trials. And get this, a huge reason they even made it to Phase 1 relies on a totally unlikely hero. The hamster. Seriously, the same fluffy creatures running on wheels in a pet store. For a long time, researchers just didn't have a good way to test if a vaccine would actually stop the severe human version of the disease, which is called hantavirus pulmonary syndrome. But Hooper's team managed to develop a highly realistic hamster model that perfectly mimics lethal HPS. This was a massive game changer. It gave them a reliable animal model to test both vaccines and therapeutics, and it really paved the way for testing neutralizing antibodies.
And the good news is, the DNA vaccine they developed, it actually works in humans. Think of it like building a biological military shield. It successfully induces neutralizing antibodies to block the viral attack. But of course, there's a logistical catch. Constructing that shield requires 3 distinct doses. You need 1 prime dose, followed by 2 separate boosters. And as you can imagine, trying to deliver a 3-dose regimen during an unexpected, rapidly moving outbreak is incredibly difficult.
This perfectly sets up our biggest roadblock, the Phase 3 paradox. Because as it turns out, that complex dosing schedule isn't even the biggest hurdle here. The science is fundamentally sound, but real-world logistics are throwing up a massive roadblock. As virologist Jay Hooper notes, to meet the requirements for licensing the vaccine requires some, quote, more creative approaches. Why? Well, because the standard textbook way we approve vaccines, the massive Phase 3 clinical trial, is essentially impossible for the Andes virus.
We are staring down a brutal catch-22. First off, rarity. Despite its deadly nature, human cases of the Andes virus are statistically super rare. Second, geography. Outbreaks are completely scattered. You get a few people in Argentina, maybe a cruise ship out at sea. Third, testing. Because of that rarity and that geographic spread, there is absolutely no obvious concentrated region to even run a classic Phase 3 trial. I mean, you can't just vaccinate 30,000 people in one city and wait to see if it protects them, because the virus might not show up there for a decade. And finally, because it's so rare, there is a major lack of funding for the extremely expensive advanced development you need to push it over the finish line. So, what do you do? How do you prove a vaccine works if you literally can't run a traditional trial? Well, you get creative. Researchers are actually taking neutralizing antibodies from humans who have safely received the experimental vaccine, and they are injecting those human antibodies into that specialized hamster model we talked about earlier. Then they expose the hamsters to the lethal virus to see if the human antibodies protect them. It's brilliant. It's a highly unconventional way to prove efficacy without needing a massive, basically impossible human field trial.
Which leaves us with this final, incredibly provocative question. How do we, as a global society, prepare for the next deadly outbreak when the cure is stalled by its own rarity? We have a virus with a fatality rate of up to 50% that can spread human to human. We have scientists who have spent 30 years building a vaccine that works. But just because the virus hasn't caused a massive global pandemic yet, the vaccine is trapped in an economic and regulatory bottleneck. It forces us to ask, shouldn't we change how we fund and license vaccines for these rare, high-consequence pathogens before they mutate, rather than always scrambling to catch up after the death toll rises? It's definitely something to think deeply about. Thanks for joining me for this explainer. I really hope this helped unpack the science and the true stakes of the hantavirus threat. Keep learning, and I'll catch you next time.